Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 23, 2025, about 3 days ago. The big result is a hierarchical memory system for robot control that retrieves key visual frames so robots remember minutes of context, beating long history baselines by about 34% and reaching over 90% on task metrics. The paper is titled MemER, Scaling Up Memory for Robot Control via Experience Retrieval. And as we'll see later, the implications for long horizon autonomy are quite significant. This paper uses a two-level policy that selects and tracks keyframes, consolidates them into a compact 8-frame memory, and keeps latency low compared with slow API models. The intro sketched the motivation and the two-level design. Figure 1 shows the overall pipeline, so an overview box helps frame the 3 panels. The left panel highlights minimal data, with about 50 demonstrations per task feeding the system. The middle panel depicts the hierarchy. A high-level QN 2.5 volts L selects visual keyframes into memory and issues subtasks, while a low-level Pi 0.5 executes actions. The right panel illustrates closed-loop control, where memory guides subtask text, and the controller outputs motion deltas. Alright, the previous figure sketched the pipeline. Figure 2 diagrams the flow that makes memory actionable. Recent frames, the task instruction, and selected keyframes feed a high-level policy, which outputs a language subtask and candidate keyframes. A keyframe filter consolidates those candidates so the memory stays compact. The low-level controller then consumes the subtask, the current image, and joint states to produce actions, keeping control responsive over long horizons. Okay, the previous figure outlined the flow. Figure 3 explains how nominated frames become a compact memory. The upper panels depict recent context windows, where orange boxes mark candidate keyframes across successive time steps. Along the bottom timeline, colored bars show nomination counts, and nearby timestamps are grouped with a merge distance of 5 frames. On the right, 3 example frames with different vote counts collapse to the median timestamp, so a single representative frame is added to memory. Well, the previous figure explained memory consolidation. Figure 5 reports task progress across object search, counting, and dust and replace, plus the overall average. The memory approach reaches about 96 to 97%, which matches the human high-level policy, while the long history baseline trails near 62% and the short history near 52%. The no history policy lags around 28% and shows wide variance, so compact visual memory clearly pays off. So, the previous figure compared overall progress. Figure 4 illustrates the evaluation suite, which spans 3 domains and spells out tasks, subtasks, and example robot executions. The top section presents object search, where subtasks guide which bin to inspect and when to retrieve an item, so memory of inspected bins matters. The middle section covers counting, which requires tracking repeated scoops across bowls. The bottom section details dust and replace, which demands remembering original locations while interleaving cleaning steps. Alright, the previous figure summarized the tasks. Table 1 presents detailed main results across the 3 domains, with arrows indicating whether higher or lower is better. In the object search columns, the memory system retrieved 59 objects and followed the optimal path 57 times, clearly ahead of the history baselines. The counting column shows just 1 wrong scoop versus 61 for no history. In the dust and replace columns, scores reached 20, 19, 18, and 20, matching the human high-level policy. Wrapping up, 2 takeaways stand out. A lightweight hierarchical policy that retrieves and consolidates key visual frames gives robots minutes of reliable memory, and it does so with low latency and only about 50 demos per task. The broader implication is practical long-horizon autonomy, where episodic memory becomes a deployable system component. Thanks for listening. I am Alex, and this was the AI Research Roundup.